Okay, guys, good morning to all of you. And Sword, Sword is here. It's good to see you here, Sword. What's wrong with you, Sword? Yes, Sword.
Yes.
What's wrong? You haven't submitted homework for your math classes.
I always forget.
You always forget.
I will submit it when I finish today's homework together.
Your classmates tell you about what I told them yesterday, because yesterday I had a math class and you were not there. So I informed them about your grading, how I'm going to calculate your grades using Edmodo. All the homework or the work that you are doing on Edmodo, that is where your certificate will probably come from, okay?
Okay.
So you have to take it serious. You cannot joke with that. Okay, everyone is here, so we will move straight to what we are supposed to be doing today. I'm going to do a presentation. It may take a while. Do you all have your notebooks? Because you need to solve some problems as well. So have notebooks and your pens, and you will solve some problems before we look at them, okay? Okay. I'm going to do a PowerPoint presentation today. We will briefly review the separating variables for differential equations. This is something you have done several times, and it was included in the prerequisite test yesterday that I asked you to solve yesterday. We will also see a new type of differential equations that can have exact factors. And then we will try to use integrating factors to solve differential equations. Here are some of the things you need to be able to do in order to complete this part of the course, which I'm sure you have done. You have already done integration by parts, substitution, and trigonometric functions. You have already solved differential equations by separating variables, and you already know about implicit differentiation. Okay, please write this down, solve it very quickly. You have this equation, x squared dy dx equal y plus 1. When x is 1, y is 0. You can solve it very quickly. Okay, we can move on. As we know, to solve this differential equation, which we know we simply treat the x as a variable itself, and we put all the y terms on the left-hand side, put all the x terms on the right-hand side, and then we integrate. Yesterday, I was looking at your homework. I saw somebody try to integrate this from here before arranging. You have to first do this arrangement before you add this integral sign, okay? And then when you integrate, you get that. Then you put in your boundary conditions or your initial conditions. And so you get your function in terms of x. There is a second problem. Solve this one very quickly, please. Okay, Shanti, you have solved it. What is the first thing you should do here?
What? I was a bit late.
You were a little bit late.
Yeah.
Solve this differential equation. Use the same initial conditions, okay? Dear, what's the first thing you do?
Rearrangement.
Huh?
Rearrange.
So what did you get?
Take e power x times e power y equal to y dy dx, and
Very good.
take e power y
You
to
first put this
the
as
right
e raised to
side.
the power x times e raised to the power y, right? Equal that. And then you move the e raised to the power y with the y terms together and the x terms together, right?
Yes.
And then you integrate.
Yeah.
And then you can put in your initial conditions now to get C. And so you can rearrange. Okay. There is more we should be doing. There is another differential equation here that you need to solve. Try to solve this one. Ruby, did you get a solution?
No.
Shanti, did you get a solution?
Not yet.
No. Anna, did you get a solution?
Not yet.
Not yet. If you are trying to arrange it so that the x's are on one side and the y's are on the other side, that's impossible. Okay? It's impossible to solve this by separating variables. You look carefully. It's impossible to have all the y's on one side and all the x's on the other side. But look at this equation from the left-hand side carefully. What is this? You will see that this left-hand side is a derivative of a product. You have x squared dy on dx plus 2xy. So they have differentiated something here. So this is a product derivative. So it's a derivative of g of x times f of x, something like that. What is the product here? What is the product how that has been differentiated to get this? Can anybody talk about that? Ryan? Ryan,
No.
you cannot think of the product. This, if you differentiate x squared times y, you are going to get this, right? To differentiate x squared times y, you leave x squared, you differentiate y, and then you leave y, you differentiate x squared, you get 2x. So x squared times y is the product that has been differentiated to get this left-hand side. All right? So it means that we can write this equation like this. Instead of writing it that way, that x squared dy dx plus 2xy equal that, we can just write it like g of dx of x squared y equal 3 sine x. All right? And now, if you differentiate something and you get 3 sine x, it means that this something should be integral of 3 sine x, right? You differentiated a function to get 3 sine x, so the function must be integral of 3 sine x, right? And so you can have your solution very clearly as you have there. So that is the solution to that differential equation. This is what we call exact integral or something, product integral, exact product integral. Look at this one, it is the same thing. This is also the derivative of some product. You can think about what product it is. What is that product that has been differentiated to get that? Sort. What is the product sort? No idea. Oh, is sort there?
X squared divided by y.
X squared divided by y. Yes. Negative x squared on y. We'll give you that. So you have d on dx over negative x squared over y should be 1 over x. And so negative x squared over y should be integral of 1 over x plus c, which is ln x plus c. If you have initial conditions, you substitute. If there are no initial conditions, then your problem remains as it is. So any initial conditions there are substituted. Okay. We were able to solve these two differential equations because the left-hand side was an exact derivative. Right? These are the two equations we have solved because the left-hand side are exact derivatives of some product. But in many differential equations, you are not going to have the left-hand side as an exact derivative of some product. Many differential equations that you cannot separate the variables. For example, this one. This left-hand side is not an exact product of something. But since we already know that if the left-hand side is an exact product, then it's very easy to solve. We are going to try to make the left-hand side an exact product, okay? So we should try to multiply it by something to give it an exact derivative. What is that thing to multiply? If we multiply by x, you realize if we multiply by x, then this will be the derivative of a product. It's the derivative of xy, right? So we have multiplied this whole equation by x to get this one. And then this left-hand side now becomes an exact derivative. The x that we use to multiply the whole equation with is called an integrating factor. A factor that we use to integrate, we will use to integrate. Now, it will be very easy. Sorry. It will be very easy to solve this. Right? Now that we have this, it's just d on dx of xy equal to x squared. And so we can solve it much easily without any problem. Now, we were able to find the integrating factor in the previous example very easily. We can use our intuition to see that if we multiply by something, we will get an exact derivative. But it is not always going to be so obvious to see that you should multiply by something to get an exact derivative. So we need to find some sort of a formula to find the exact derivative. Okay? So in this, in the rest of the presentation, I'm going to derive the formula that we use to find the exact derivative. And then you will use that formula to solve differential equations of the form that we have here. Let's say you have a first order differential equation of this form, dy on dx plus y times some function of x equals some function of x. Remember the form in which this differential equation is. The coefficient of dy dx is 1. So if the coefficient of dy dx is different from 1, you have to divide by that coefficient to get the coefficient of dy dx as 1, and then plus y times some function of x equal q of x. Let's multiply by some integrating factor. Let's just say our integrating factor is f of x. And then we want to multiply it by f of x. And then we will find f of x. What is f of x? So we multiply all through by f of x to get an exact derivative on this left-hand side. This left-hand side becomes an exact derivative. This means that this term is one derivative of that exact derivative, and this other term is the second derivative of the product. So you can easily see from here that here we keep f of x constant, then we differentiate y to get dy dx, and then in this term we keep y constant, and then we differentiate f of x to get f of x times p of x. All right? So the first term we get by differentiating y f of x. So we want to find the second term. This is our first term. When we differentiate y f of x, we get the first term, which is f of x times dy dx. And then the second term is y f prime of x. And y f prime of x should be this. All right? That means that p should be equal to f prime of s or x over f of x. Remember, we are trying to find f of x, not p of x. And so in this case, we have to try to integrate and see. If we integrate, we have integral of f prime of x all over f of x dx. Remember, this integral here can be easily solved, right? if you have integral of f prime of x over f of x, just know it's natural log of f of x, right? So that just will be natural log of f of x, actually absolute value of f of x. And then from here, we can find f of x. So our f of x will be e raised to the power integral of p of x dx. You will find here that we have ignored the constant in this case because the constant is arbitrary. The constant could also be 0. So that's why we ignored it here. We are finding the simplest integrating factor, simplest. So, and this would be the simplest one. So this is the formula that you use to find integrating factors. Just that. F of x is e raised to the power integral of p of x dx. Always remember the form of your differential equation should be dy on dx plus y times p of x equals something q of x, some function of x. And so you take the coefficient of y, dy dx, the coefficient is 1, and the coefficient of y, what did I say? Let me see. So your function should always be in this form, dy dx plus y times p of x, some function of x, should be equal to some other function of x. If your coefficient of dy dx, let's say you have a function, say you have 2x dy dx plus y times x cubed, for instance, equal 5 over x. If you have a function like this, you must first make the coefficient of dy dx to be 1. So you must divide by 2x here. So you have dy dx plus y times y over 2 times x squared equal 5 over 2x squared. So you have to rearrange your problem like that. And then now it's easy to find the integrating factor from here. Now it's easy to find your integrating factor from here. So this whole thing here, x squared over 2 will be your p of x. And so your integrating factor will be e raised to the power integral of x squared over 2 dx. You just integrate that and then you can find your integrating factor. So in the future, instead of writing integrating factor as f of x, we will use I. We will say I, the integrating factor, is equal to this. Okay? So remember that integrating factor. So example, we want to find x, we want to solve x dy dx plus 3y equal e raised to the power x over x squared. So we have to make the coefficient of dy dx to be 1. So we divide by x to get what you have there. And then our integrating factor should be, our integrating factor should be 3 e raised to the power integral of 3 over x, the coefficient of y here. And so if you integrate that, you get e raised to the power 3 ln x. We have to make it as simple as possible 3 raised to the power 3 times ln x is the same as 3 times e raised to the power ln x cubed, right? And e raised to the power ln x cubed is just x cubed. So we multiply by our whole function by x cubed. And then you just find that your left-hand side now will just be d over dx of x cubed times y. Even though I included this step, you multiply by x cubed. After you find your integrating factor, just know that the left-hand side of your equation will be something like d over dx of your integrating factor times y equals some function on the right. So after you arrange, you will always have this. And so your x cubed y should be integral of e raised to the power x dx, which should give you e raised to the power x plus c, and you can solve for y. Okay? You guys should try this second problem before I move on with it. Just find the integrating factor first. Find the integrating factor very quickly. What is the integrating factor? Let me hear from someone. Anna, you haven't said anything today.
Hmm. Yes. Well,
Did you
you
get that
put
as
it
the
up
integrating
also.
factor?
Yes.
Okay. And so you multiply all through by sine x, then you should get that. So d over dx of sine x times y. Always know that when you multiply all through by the integrating factor, the left-hand side will be this exact derivative, integral of integrating factor times y. Always, integral of integrating factor times y. Okay, here are more questions for you guys to solve. We have 10 minutes to go. Solve these two. I only need your final answer. For the first problem, you should get y equals cx minus 1 over 2x, where c is some arbitrary constant because you don't have any initial conditions there. For the second problem, you should get y equal to x minus 1 e raised to the power x plus 2 e raised to the power negative x. Because you have initial conditions there, you don't need to have any c in it. Okay, that is it for our class today. You will try question exercise 24a, question 1 to question 9 today. It's all about integrating factors, so it should be very easy to solve. Okay? Sheshe ni men. See you.